Presentation number 3, we've got a friend from the Wisconsin DOT, our Midwest partners. The partnerships have really made an effort over the last few years to have a little bit of cross-pollination. We're sending DOT reps to the various meetings because we really do see a lot of value in these. And so great to have a friend from Wisconsin with us. So the presentation is going to be the Midwest Bridge Element Deterioration, TPF-5. Presenter is Philip Meinel. He's the Structures Asset Management Engineer, again with Wisconsin DOT. So let's welcome Philip.
All right, thanks for having me here. And I think I could have paid Casey and Nick to make that presentation right before mine. So this study came out of some work we did in 2018 with early data from our AASHTO element data and trying to fit deterioration curves for each of our wearing surfaces. So in Wisconsin, we track each of our wearing surfaces as an agency-defined element. And realizing at that time we needed a whole lot more data to come up with curves that we felt more comfortable with. So my predecessor, Bill Oliva, a big part of bridge preservation, was integral in bringing all of these states together. There were 12 states that participated in this study, and the principal investigator was WSP. The research objective was to pool our resources and our data. A lot of times we talk about what we're doing state to state, and we're like, yeah, we agree, we're pretty much doing it the same. And then you dive into our databases and you try to merge that, and all of a sudden you find a bunch of differences. So there's a lot of work. Initially this was a 2-year study, ended up taking 3 years. We wanted to develop reliable deterioration curves, both for component MBI ratings, but then also quickly getting into the element level for our bridge management systems. And that is the final goal, to increase the accuracy of our bridge management systems, whether that be BRM, agile assets, or custom programs. So here's a list of tasks. Traditional literature review, going from a raw data set of just collecting information from everyone, changing that into an analysis data set, and then creating models, and then reviewing those models. So like always, you want it to just be a linear progression, but as we kept going through our tasks, you kept having to circle back, trying to reevaluate the data, and figure out exactly what we were looking at. So for the literature review, I'm going to go over this pretty quickly. If somebody wants to talk deterioration modeling after this, I'm all for that. So this is traditional Markov modeling, and you can see the different modifications you can make to the curve with the viable factor, protection factors, environmental factors, stuff like that. These are three key aspects of the modeling. So the linear regression, just figuring out the transition probabilities, going from one condition state to another. The Florida one-step method, so that greatly simplifies the Markov deterioration from like a full matrix of probabilities down to essentially a one-step through that matrix, progressing from one condition state to another. And then maximum likelihood is used for the viable factor. I'll touch more on that later. So here's some stats of the data that we gathered from the states. So almost 220,000 bridges amongst 12 states, almost 2 million routine inspections with MBI data, about 400,000 routine inspections with AASHTO elements. Only about 100,000 routine inspections with AASHTO element defects. We had about 200,000 construction activity records. We were hoping for a larger data set there, but there were unfortunately, there was a lot of holes in our construction history of what's actually been done to our bridges, state to state. So that affected how we went through that modeling process. Almost 9,000, or over 9,000 NDE inspections were also gathered, and between this, among the states, almost 400 agency-defined elements. We also collected from the states, sorry, I need to scroll on my notes. We also collected information about inspection practices, element definitions, coding methods, construction activity, preservation and maintenance policies. So trying to understand that data that we were gathering instead of just pulling data in, running it through an algorithm, and then spitting out results. We wanted to make sure we understood the data that we were processing. So the analysis data set used a lot of this similar table structure as BRM. That was the majority of Midwest states' optimizer that they were using for their bridge management system. Quickly touching on data governance here. So Wisconsin is the data custodian for the data set. All of the participating states had access to the final results, but we want to maintain this database over time so that we can use it over and over again, update it, create new curves for various elements and defects. So again, the three basic formats of the deterioration results. First off, Markov, that was used for the majority of the results, and then viable factor to manipulate those Markov deterioration curves, and then action effectiveness used a maximum likelihood estimation as well. So the Markov procedure, essentially you have the refined analysis data set. You're going to use SQL statements to create inspection pairs out of that data set, then incorporate work activities into that data set. So if you have an inspection pair with an activity that occurred in between those inspections, you're going to filter that out normally. And then we also stratified the data set with specific inventory values. So if you were looking at a specific aspect of your bridge that you wanted to know more about the deterioration of that specific type of bridge, you could get to that level of granularity. And then the major deliverable were Excel spreadsheets that you could manipulate with pivot tables to find what you were looking for. So we broke the study into these different tiers. We were trying to do a lot with this study, so the tier method was kind of, if we weren't happy with what the contractor was doing, we could boot them off at any time and find a different contractor. So we didn't have to do that, thankfully. But tier one, we would go after the MBI rating deterioration. Wisconsin wasn't necessarily looking for that. We're comfortable with what we had, but there are a lot of other states that just wanted to get a better handle on their NBI deterioration. And then also with tier one, we wanted to get right into the roof of our structure, what I think is the most important part of our structure, and the key to bridge preservation are reinforced concrete deck and reinforced concrete slab. And then tier two went into more granular elements. So here's some of the results. Component NBI deterioration. So since we had so many NBI inspections, we did take a random sampling of what we had, but we did constrain that to be state-owned structures, bridges with traffic, and non-buried structures. So more of the sample set that everybody was interested in. And here you can see a graph of the results. You got culvert, NBI deterioration at the top in gray, substructure in blue, superstructure in red, and deck NBI deterioration in yellow. So with stratifying the data based on inventory values, we can do refine the models a little bit more. So here I just broke out decks that had epoxy coated rebar in green, and you can see their performance compared to decks with black bar. Here's Superstructure NBI, and then I broke it out by span type. So pre-stressed girder in gray, reinforced concrete slab in red, and steel girder in blue. Reinforced concrete slab ratings. So here I was looking at, we currently have an inspection policy where deck NBI and super NBI should be the same for reinforced concrete slab. So I was just interested to see what the data showed. Here I plotted reinforced concrete slab for both the deck NBI and super NBI, and there's a little bit of a difference there, and I'm told historically we did not collect them with the same NBI, so that probably is the explanation there. So here's getting into a bunch of different tables. So showing the transition time from condition state 1 to 2, that T1, 2, and then median transition time for condition state 2 to 3, T2, 3, and so on. The first chart there, we basically took two random samplings, group 1 and group 2, based on the column on the left there, and looked to see if the data was I guess homogeneous or the same throughout. So those, you can see the transition times for both of those random samplings are very similar. So the researcher concluded that the results were statistically valid. Also showing a breakout of transition times based on construction era, traffic volume, but that table on the top right really shows the value of this study and pooling our resources together. You can see a large variance in the transition time state to state, but when we pool our data together, you get some better results at the end. And then at the bottom there is the overall results for reinforced concrete deck element, the overall average, but then also the unprotected value for decks without a wearing surface. We generated a viable factor for a reinforced concrete deck element. Here you can see all of the different data points plotted on an age graph. The gray data points were considered outliers. The blue were used to develop the viable factor. And then you can see that plotted against the average. Here are results for reinforced concrete slab element. Just plotted out reinforced concrete deck versus reinforced concrete slab, and you can see reinforced concrete slab outperforming reinforced concrete deck. Just for fun, I went back to our NBI results, and it's nice when our data sets confirm each other. So both the NBI rating and the element rating confirm that our RC slabs outperform our RC decks as expected. The last part of Tier 1, we took a little bit of a detour here looking at the residual effects of preserving our decks. So these are both do-nothing deterioration curves, but it shows a residual effect, a benefit for performing routine preservation on our decks. So Tier 2, a little bit different mentality here, diving deeper. I just want to highlight this. Bridge components are really good for getting a general idea of structure condition. It helps with our communication, helps with funding discussions. Bridge elements, though, help us understand where we need to perform the work on our structures. And then element defects help us understand what work needs to be done on those elements on our structures. In Wisconsin, we really look at elements and defects as the key to an automated bridge management system that is focused on bridge preservation. So here's some results from Tier 2. This is what I was excited to get into, the wearing surfaces. Here's a general graph of reinforced concrete deck deterioration with the wearing surface at the top in orange, reinforced concrete deck that's unprotected in gray, and then the deterioration for all wearing surfaces in yellow. And that last wearing surface deterioration is not very helpful because we know that our overlays deteriorate at very different rates. And so that's why we dug into this area in a little bit more detail. So we created research groupings for wearing surfaces. It was really helpful if agencies had defined elements for their wearing surfaces, but not all agencies collected that. So we did have to translate from NBI item 108. You would think it would be the same for all states, but there are nuances in there about what inspectors used for which wearing surface. So it wasn't the same translation for each state. Here's the straight Markov deterioration for a handful of different wearing surfaces. We generated one viable factor for all wearing surfaces. Again, hoping to gather more data throughout time to have a unique viable factor for each wearing surface in the future. But here you can see between the straight Markov and the adjusted viable factor, it does make a significant difference in the deterioration. And here's a breakout of just each condition state and the quantities, what they're doing over time. Tier 2 also had joint deterioration. The researcher noted that joints deteriorated a little bit faster than originally expected. Again, we generated a viable factor for all joints, and that viable factor was around 4. This part of the research was kind of out there, but it was something that a question we've asked in Wisconsin. How can we better predict in the future what our structural elements are going to look like? So here we looked at defect progression. So going from cracking, reinforced concrete cracking, to reinforced concrete delamination. It's a little confusing. The column on the left there where it says defect 1130 for cracking, there's these different values. That was basically a health index to try to pull the cracking condition all into one number. So as you can see, there is kind of a health index with 100% of CS1 plus 2/3 CS2 plus 1/3 CS3. The vast majority of the decks without delamination stayed in that condition, so that obviously very slow development for this defect. So that limited the data that we had available. Again, not all states collected defect data, so we were limited there as well. But the relationship with deck cracking behaved as expected. And I'll get a little bit more explanation here. So where it says up to 1.0, if you look at only condition state 2 for cracking, that's like 6%, up to 6% of your element has CS2 cracking. That's the least likely to develop delamination. You can see a transition time from 1 to 2 at around 31 years for 50% of that to move to the next condition state. If you go to the next value of up to 0.98, that's anywhere from 6 to 60% of your element has CS2 cracking, and lo and behold, it's 2 times more likely to develop defects or delaminations. So it's what we already know, it's intuitive. There currently isn't a bridge management system that can process this information right now, but it was a question that we wanted to investigate. I think it has potential for the future, so kind of laying the groundwork in this area. We also looked into paint deterioration. Didn't get an exact deterioration for paint effectiveness, but again, looked at correlations between paint and steel girder corrosion. For reinforced concrete substructures, here you can see transition times for various reinforced concrete substructure elements, and they're all very similar except for columns. And the researcher noted column data is collected by each, and so when we're looking at bridge element deterioration, how we collect the data really matters, right? So I would assume that if columns were collected on more of a linear foot basis, you'd see a more similar transition time among the substructure elements. We also we were looking for substructures that were in harsh environments and how they deteriorated different from our typical substructures. So here you can see a significant change in transition times when the ADT under the structure is greater than 10,000. Tier 3 of the study got into identifying all of the agency-defined elements among our states, determining which elements to advance further, providing guidance on data collection, gathering, formatting, determine the status of NDE efforts among the states, and then how do those NDE results translate into concrete bridge deck inspections. So here's a list of states that collect wearing surface elements and states that do not. Here's a graphic out of Wisconsin's field inspection manual. So we realized early on with our automated bridge management system, the optimizer needs to see both the top and bottom of our deck and slab. So if we've got something going on top, we're more looking at an overlay. If we've got something on the bottom where it shows deterioration all the way through that element, then we're looking at a redeck. And we do that intuitively when we're looking through inspection reports, but we need it in the data so that our optimizer can tell the difference. So in Wisconsin, even if you have an integral wearing surface, just a bare deck, we will code that as a bare wearing surface just so that we can tell the difference of when to perform a concrete overlay or redeck a structure. Here's a list of states that collect defects and don't collect defects, and just a snapshot of Wisconsin inspection manual showing our defects that we use for reinforced concrete. When we got into NDE, we didn't have a whole lot of data outside of Wisconsin. So Wisconsin has a regular program for monitoring our bridge decks with NDE. So most of the NDE use was limited to as needed or on a research basis. So here's some graphs showing breakouts of Wisconsin NDE. Most of it is thermography. There's also GPR, chloride ion testing, and chaining in there as well. So, but we did get results back from Illinois, Indiana, Nebraska, along with Wisconsin data. 2 minutes. So here is how Wisconsin translates NDE defects into bridge element condition. So again, we're recording that defect under the specific wearing surface element. So when you're talking about going in and figuring out how this specific wearing surface deteriorates, we can just pull up our agency-defined element, look at the specific defect of interest, and pull that data together. So 2 main recommendations coming out of Tier 3 is that states could work on a more uniform way of assessing deck condition. A lot of the states, as we were having these discussions, understood the intuitive value of having the wearing surface broken out separately, and a lot of states said they would probably be looking to do that in the future. The other thing was the format of the treatment or construction history on each of our structures, recording exactly what we're doing on our structures and in what year is very helpful for deterioration. So for implementation, again, a lot of it was geared towards BRM. Here's a graph out of BRM. Some results are too advanced for current BMS software. The models can be stratified, but you do need to be careful that you don't limit the data set too far that your results become invalid. The data model can be updated. We can also generate additional models for additional elements. We didn't include all elements in this research project, but we did set up the process so that we can repeat it for each element of interest. And then states are going through the process right now of comparing their existing BMS settings to the new settings with these new deterioration curves. For future research, obviously updating the data and refining deterioration models. Additional data cleaning efforts can be done always with all data sets, but if we can better align our data collection practices, we can help minimize that work. We can work on an improved understanding of the differences among our 12 agencies and their element deterioration rates. We could look for improvements in the quality and condition and consistency of our construction activity data, like I mentioned before. Further the development of defect data and associated models. At one point, the researcher had mentioned like the defects were never intended for deterioration modeling. And my question back to him is, why? Just because we haven't? But understanding how those different defects develop over time, I think will really help us better predict what to do on our structures. And then, yeah, producing best practice guidance and implementation. So with that, thank you.
All right.
Is the work complete, Philip, or are you continuing? Is the TPF still, is the pool fund study still open in terms of collecting money and continuing to do some of those other steps?
No, it is closed, yeah. If I'm remembering correctly, we wrapped it up November last year. So the report is out there. We actually have a separate contract with WSP, so we are doing more diving into the data from Wisconsin's perspective, and other states are doing the same with other entities that they have access to, and then we're sharing notes.
All right. Let's thank Philip one more time.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.